Let's take a look now at this example. We want to simplify the radical expressions first and then add together any of the radicals that are like radicals. And as you know, a like radical means that you will have the same index, which all three of these have because they're all square roots. Index is 2. And then the same radicand. The radicand is what's inside the radical. And as you can see, these three right now do not look like they're like radicals. So that's why you want to simplify each first. So let's take a look at the first one here, which is the 128 x to the 10th y cubed. So let me rewrite that here. 128 x 10 y 13. And we're taking the square root of that. As we've done in the past, we're going to do a factor tree on the coefficient. Try to look for perfect squares, and since 128 is even, I know a 2 goes in, and 2 divides into 128 64 times. And now I have located my perfect square. We could continue doing a tree on 64, but we know that the square root of 64 is 8. We're going to take the square root of 64, that's going to be an 8, and then this extra square root of 2 is going to stay inside the square root. Now we're going to look at x to the 10th, and if you recall from previous work that we've done, x to the 10, there are 10 x's, right? And we have talked about the fact that we're looking for pairs of x's. And so, because a pair of x's, x times x is x squared. So that's a perfect square. So how many x squares are here in x to the 10? Well, there are 5. So the square root of x to the 10 is x to the 5, because there are 5x squares in x to the 10. So nothing left over in the radical for that. And then y13, how many pairs can we make from y13? Well, we can make 6 pairs of 2 each, which is 12. So we have y squared, and we have that 6 of those, right? I'm going to just write them this way. So there's 12 y's there, okay? And then we have an extra y. So the square root is y to the 6 groups of y squares, right? And 1 extra y. So for our first term, we have the square root of 64. Let's highlight that. The square root of 64, so that's an 8. And then we have this square root of 2 that's left inside. I'm going to leave some room. Then for the y10, that's a perfect square, and its square root is x to the 5, x to the 5th. And for the y13, we have y to the 6 square root of y. So y to the 6, and then the y that stays in with the root 2. All right, so that's our first term. Now we're going to go to the second term. Let's change that color. And we have negative 2, but now this is a cube root. Oh, did you catch on to that? The index is 3, so we're looking for perfect cubes. So 2x to the 15th, y to the 19th. X to the 15th. We're looking for how many groups of 3 x's can we make? Because x times x times x is x cubed, right? So we can make 5 groups, right? Let's write that here. We can make 5 groups of x cubed, right? I mean, there's 5x cubes to make x to the 15th. So when we take the cube root of that, we get an x to the 5th, because we had 5 groups of 3 x's. So that x to the 5th comes out here with this negative 2. Negative 2x to the 5th. And inside the cube root, we still have the 2 from here. Nothing from the x's. All the x's, that was a perfect cube. So there were no extra x's. All right. Cube root of y to the 19th. Okay, so we're looking for how many y cubes are in y to the 19th, right? Y cubed, and there are. If you say 6, you're right, because that's 18 y's, right? So there's 18 y's here, and 1 more to make 19. And when we take the cube root, it's y to the 6 from these, and then the extra y stays in the radical. So y to the 6 and the extra y. Let me highlight that in black, because this is part of our next step later, okay? Now we need to simplify this guy. 5xy, and now we're back to square root. Did you see that? So 5xy, let's put them here. 5xy square root 2x to the 8th y 11. The square root of x to the 8th. How many groups of 2x's can we make if we have 8? How many of these x squares can we get out of x to the 8? If you said 4, you are right. The square root of x to the 8th is x to the 4th, because there are 4 x squares in x to the 8th. y11, square root of y11. How many y squares can we make out of y11? If you said 5, you're right, with the extra y, right? Because 5y squares is y to the 10th, and then there's an extra y. So the square root of y to the 11th is y to the 5th with an extra y in the radical. So we're going to take the x to the 4th here, and it's going to get multiplied times this x that's out here. Okay, and then we're going to take the y to the 5th, and it gets multiplied times that y. The 5 is still there, so we have x to the 5th and y to the 6th, square root, the 2 is still there, and then remember the extra y we had here? That goes there. Okay, so let's see what we've got going here so far. We've got 8x to the 5th y to the 6th square root of 2y minus 2x to the 5th y to the 6th cube root of 2y plus 5x to the 5th y to the 6th square root of 2y, and the like radicals are this one and this one. This one is not a like radical because of the index. Okay, so go ahead and let's an 8 plus a 5 is 13. X to the 5th y to the 6th square root of 2y. The negative 2 x to the 5th y to the 6th cube root of 2y is part of the final answer.